All right, good morning. Welcome to the lectures of PHYS 1111. Now, in the previous lecture, we already have discussed how to formulate Newton's second law in the rotational form, right? Now, let's have a brief review of what we have learned. We actually have defined the torque. The torque is just a moment of force in your high school study. In here, we define the torque as the perpendicular component of the force multiplied by the so-called moment arm. The moment arm is the point of application of the force, the distance of the point of application of the force from the pivot point. Okay, so F per multiplied by R will give you the torque or the moment of force you learned in high school. I already have mentioned that the midterm cover only to momentum and collision, not on rotation. Okay. I mentioned it before again and again. Okay. Now you can see from this definition that the torque can be expressed in terms of the force, the distance of application, and also as a factor of sine phi. The phi is the angle between the force and the radius. Okay, and the radius radial direction. Okay, so you may also consider the torque as being the line of the distance of the line of application of force with the pivot multiplied by the force itself. It just gives you the same result. Now this is how we define a torque, and we also have defined the so-called angular momentum in a similar way. Now for the torque, we multiply the perpendicular component of the force by the distance, right? And for angular momentum of a single particle, we multiply the perpendicular component. What an energy will be covered? We include up to momentum and collision, right? What an energy is before that chapter, right? Before momentum and collision. So if momentum of collision is included, of course, what an energy will be also be covered, right? Now, so we define the angular momentum like this. Okay, the perpendicular component of the linear momentum multiplied by the distance from the pivot point. Okay, now so if I define the angular momentum of a single particle like this, then for a rotating rigid body. Now for rotating rigid body, if you consider a single particle inside the body, we find that the velocity of that particle is perpendicular to the radius, perpendicular to the with the radius that's drawn the particle to the pivot point. Okay, because the particle is now under circular motion. Okay. So we can use the simple formula of V equal to R omega. And if we do so for each of the particle, then we find that the total angular momentum of all the particles in the rigid body will be equal to summation mi/ri per square multiplied by omega. But summation mi/ri per square is the moment of inertia of the body about the axis. So the angular momentum can be written as I omega, where I is the moment of inertia and omega is the angular speed. So it's just like linear momentum. For linear momentum, you have the P given by the mass multiplied by the velocity. But for angular momentum, you will have the moment of inertia multiplied by the angular velocity. So the quantity just translates to the angular counterpart. Okay. And we also have derived we use energy consideration, and we consider the application of a torque on a rotating object, and the torque actually does some work in moving the object by a small displacement, angular displacement d theta. The torque actually does the work of tau d theta, and that is translated to the increase in kinetic energy of the body. And for rotation, the kinetic energy is given by half I omega squared. So by equating the work done by the torque to the change in kinetic energy of the system, we successfully derive the Newton's second law for rotation. The torque is equal to the moment of inertia multiplied by the angular acceleration. So each of the quantity you just go translate from the linear counterpart to its rotational quantity. Okay, the force become the torque, the mass become the moment of inertia, and the linear acceleration now become the angular acceleration. Okay. Now, if you look at this formula, torque equal to I alpha, then it will become very apparent that the moment of inertia now plays the role of inertia, the reluctance of a body to change its state of motion, to change its state of rotation. And please be reminded that the moment inertia now plays a similar role as mass in linear motion, but there are important differences. The mass is an intrinsic quantity, the amount of matter in a body. That is called mass, right? But the moment of inertia has more information than that. The moment of inertia actually depends on the distribution of mass, not just the mass, but it's the distribution, the shape of the object. And also it depends on the axis of rotation. If you choose the different axis to rotate the body in along different axes, then you have different moment of inertia. Now the Newton's law of rotation is torque equal to I alpha, tau equal to I alpha. And if I write alpha as the omega dt, the alpha angular acceleration is the rate of change of the angular velocity. So we write alpha as the omega dt. And if I put the I inside the derivative, if I assume I to be a constant and I put it inside the derivative, I can identify the combination I omega as the angular momentum. So I arrive in a form of Newton's second law of rotation in terms of the angular momentum. The torque is now equal to the rate of change of the angular momentum, where the angular momentum is given by I omega. Okay. Now, although I have said that, there are actually a very important difference, the major difference between the two forms of Newton's law of rotation. The first form is tau equal to I alpha. The second form is tau equal to ddt I omega, right? Or ddt the angular momentum L. Okay. Now you can see in the second form, which we have just arrived, the derivative also acts on the moment of inertia, right? Instead of just acting on the angular velocity, it also acts on the I. And we assume that the I is a constant, and so we put it inside the derivative. But that direction is not correct if the body is not a rigid body. Can you see that? Now, I is well defined for a rigid body. It does not change, right? For rigid body, you calculate summation MRI per square. You always have a certain value of that quantity when you are talking about the rotation about a given axis, because the body cannot deform, right? But there are situations in which the body can be deformed. In fact, many of the objects we encounter in our daily life are not rigid body. For example, this book is not a rigid body. You can flip it around, right? This is not rigid. And I don't know if you have seen the skater on the television. When the skater rotates, okay, a spin, when they say a spin about an axis on her body, when she contracts her arms and her legs, she's getting spinning faster. Okay, and that is the a consequence of an important law called conservation of angular momentum. We will learn in later. Okay. Now, but for this case, it is clear that the moment of inertia of the body has changed, because when the skater contracts her arms and contracts her legs, the distance between the particle in her arms and her legs with the axis of rotation has now decreased, right? So the moment of inertia does change. And if that is the case, then this form of Newton's second law will not be the same as this form, because the derivative now also acts on the moment of inertia, not only the angular velocity, right? So this form will not be the same as the form tau equal to I alpha, because we have now the derivative has two variable, two object to act. It acts not only on omega but also on I. Now the question is, we haven't derived Newton's second law in this form if I changes. Okay, we just assert that, we just assume that I is a constant, right? And we put the I into the derivative. But for the case with I changing, we haven't derived this form of Newton's second law, right? For I changing, that putting the I into the derivative is not trivial. It requires some proof that goes beyond what we have just discussed, right? So the question is whether this form is correct if I changes. Okay. Now the answer is this form of Newton's second law is in fact correct, even if the body is not a rigid body, even if I does changes. Okay. Now this is seems to be a miracle. We haven't proved it, and we left the proof to the end of this chapter when we have more time to discuss the more formal mathematics of this problem. Now the proof is by no means easy, so I better leave it at the end as an extension. But believe me, okay, even with the I is changing and the body is not a rigid body, this form of Newton's second law for rotation still hold. So the torque is in fact can be written as the time derivative of the angular momentum. The angular momentum is I omega, where I and omega may be both changing with time. Okay, so we make this assumption and we prove it later when we have the time at the end of the lecture. Now let's have a brief review in rolling without slipping. Now, do you remember this diagram? We actually have studied this diagram in chapter 2, right? A body, a circular object, like for example, a spear or a cylinder. It rolls without slipping. It rolls without slipping. Please mute your mic. Okay. A body rolls without slipping on a horizontal surface. Okay. Now, for rolling without slipping, you can see when the body rolls forward, the arc length AB, suppose the body now rotates with an angle delta theta forward. So the arc length AB, each of this point on the arc of the circular object will now be in contact with the table, right? So in rotating the by angle delta theta, the body actually has advanced by a distance of delta S, where delta S is just the arc length subtained by the angle delta theta. Okay, this arc length, the arc length obtained by AB, which is obtained by the angle delta theta, is just the same as the distance moved forward by the center of mass of the object. Okay, so in that case, we can write delta S, because it's arc length, we can write delta S as R delta theta. And we divide by, when we divide the equation by the delta t, and we take the limit delta t tends to 0, then we find that the s dt is equal to r d theta d omega, d theta dt. D theta dt is of course the angular velocity of the object, so we write it as omega. But the s dt is actually the velocity of the center of mass. Okay, because we are now locating the position for the center of mass, and we find that it advances a distance delta s in the time delta t. So the SDT we can write as capital V, which is the velocity of the center of mass. So we now have an expression relating the velocity of the center of mass of a rolling body with the angular speed. Okay, V is just equal to R omega. Now note that we use the capital V but not small v for in the formula, because V now refer to the center of mass velocity, not the velocity at the rim of the circular object. Okay, do you notice the difference? Okay, so it's important to notice that we now refer to the translational velocity of the object as a whole. Okay. Now we can also think of the rolling body, a body that rolls without slipping on the horizontal surface. We can think of that motion as a combination of two motions. Okay, the first motion is that the body now rotates about its center of mass with angular velocity omega. So that is a pure rotation without translational motion. The second motion is the body as a whole move relative to the horizontal surface with a velocity equal to big V. The big V is the velocity of the center of mass. So a rolling without slipping on the horizontal surface can be thought of a combination of these two motions. The first motion is the pure rotation about the center of mass. The second motion is the translational motion of the center of mass relative to the table. So when combining these two motions, we have a pure rolling. We have a rolling of that circular object along the horizontal table. Okay, so now let's consider the first motion. The first motion is a pure rotation about the center of mass. So if you look at the rim, the rim of the circular object, you will find that this particle will be undergoing a circular motion around the center of mass. And therefore, by the simple equation between the angular velocity and the linear velocity, we find that this particle will have a linear velocity of capital R omega, where R is a radius of the circular object, right? Now you see that because the object is rotating in this figure in the anti-clockwise direction. So the velocity in each of this point will be something like this, right? It goes around in the clockwise, the center as in the clockwise direction. So the velocity takes on different direction. They have the same speed, but the velocity at different points, they have this different directions. Now consider this motion is now added to the translational velocity to the right. For the translational velocity, all the particles carry this velocity to the right. So if you combine the two motions, then for the red points on the rim of the circle, they will carry a velocity that is equal to the vector sum of the rotational velocity and the translational velocity. Now, but the rotational velocity, they have different direction at different points on the rim of the circle. For example, at the top of the circular object, the rotational velocity is to the right. The translational velocity is also to the right. So the sum of the two velocity will be 2r omega, because the translational velocity also has a value of r omega by our previous discussion. So at the top of the object, the total velocity of this particle is 2r omega. Is that right? Now for the particle, say at this point, at the right, the rotational part of the velocity is downwards. The translational part is to the right. So the combination of the two velocity will be in this direction. It makes the 45 degree with the horizontal. And the magnitude, because both velocity, they are equal but at right angle. So the final velocity, magnitude of the velocity will be square root 2r omega. And similarly, you can calculate the velocity on the left side. Now, the interesting point is that when you look at the point that is instantaneously in contact with the table, you'll find that the rotational part of the velocity is to the left, while the translational part is to the right, right? So if you combine the two velocity, you will find that the point that is in contact with the table is instantaneously at rest, okay? Now, that point is at rest only instantaneously, okay? When the body continues to roll, the points will go up again, okay, and will go forward. But at that instant, when it is in contact with the ground, it is somehow instantaneously at rest at that moment. Okay, so so the contact point you can see from this figure. If you examine this velocity of the different part of the body, you will find that at that instant, the whole body seems to be rotating about the contact point. Okay, so the contact point is actually the instantaneous axis of rotation through which the whole body seems to be rotating about. Okay, now but that is an instantaneous phenomenon only. When the body roll passes this point, there are other points of instantaneous contact, and the body will be instantaneously rotating about the other points, but not this point. Okay. Now, having learned so many about rotation, we want to apply what we have learned to study a rotating body. Now we have a yo-yo. I think you have already played a yo-yo before. When you release the yo-yo and let it falls under gravity, the yo-yo will be uncoiling itself. The string along the axis of the yo-yo will uncoil itself. So the yo-yo will descend, right? Now this is the axis of the yo-yo, and the string is coiled around this axis. So when you release the yo-yo falls down, but somehow it is tied by a string on the axis. So this is not a free falling, right? The falling is actually opposed by an upward tension force on a string. So we are now going to study this motion using Newton's second law for the system of particle and also Newton's second law for rotation. Now for this body, we need two equations. Why? Because we have to deal with the translational motion and the rotational motion. The translational motion comes from F equal to ma. Now the body as a whole can be considered to obey Newton's second law. The only thing that is important is that you treat this A, not the acceleration of a single particle, but the acceleration of the center of mass. In the chapter of momentum and collision, we learned that if we interpret this A as the acceleration of the center of mass, then we can apply Newton's second law to extend the body, just like what we did for a single point mass, right? So it's important to note that this A now refers to the center, the acceleration of the center of the body, and you can apply Newton's second law. Now the simple, the force are simple. We have a downward force of gravity mg. We have an upward force due to the tension. Now, although the two forces does not act on the same point, but we can still apply Newton's second law to the center of mass. So if we take the downward direction as positive, then mg minus t is equal to the net force. The net force is now equal to the mass of the yo-yo, which is small m, multiplied by the acceleration, the linear acceleration a of the center of mass. Is that right? Now we study the rotational motion about the center of the yo-yo. The force of gravity produces no net torque because the force of gravity acts directly at the center of the yo-yo. So its moment arm is 0, right? The moment depends on the force multiplied by the distance. That is the moment arm. But the moment arm is 0 because now the gravity force acts directly on the axis. So we don't have that moment. But the tension force, it does produce a moment because its line of application is at a distance r from the axis of rotation. So the torque produced by the tension force will be TR. T is the tension, R is the the radius of the axis of the axle of the yo-yo, and that becomes equal to I alpha. I is of course the moment of inertia of the yo-yo, and alpha is the angular acceleration. Now we now have two equations. One describes the translation motion, the other describes the rotational motion. Now, but when you take a look at these two equations, you find three variables. The tangent is unknown. The linear acceleration A is unknown. The angular acceleration alpha is also unknown. But you only have two equations, but you have three unknowns. So there are not enough equations to solve for all three variables. So there are some conditions missing. Okay, we have to insert another condition that allows us to solve for all the three variables. Now that condition is the no slip condition. Now when the yo-yo uncoil, when the string uncoil on the axis of the yo-yo, there will not be any slipping. So that is like what? That is like a rolling of a circular object on a table. That again produces no slipping. So that means our equation for no slipping now applies also to the yo-yo. So the linear velocity of the center of mass can now be related to the angular velocity. V equal to R omega, where V is the velocity of the center of mass, and omega is the rotational speed of the yo-yo. And they're related in this simple way, because the axle, the string, when it uncoils on the yo-yo axle, it does not slip. Okay, so the no slip condition applies, just like this case. Okay. Now, if we take the derivative on both sides, we find that the linear acceleration is for the center of mass now, is equal to R multiplied by the angular acceleration alpha. Okay. Now, so we now have an additional equation that relates A and alpha, and that provides us sufficient equation to solve all the physical quantity, because we now have three equations to solve for the three variables. And so for the rotational motion, we have T equal to I alpha over R, but alpha can be written as, by the no slip condition, it can be written as A over R. So we have T equal to I over R squared A. Now we can put this T back to the first equation. And then the first equation will contain A only. And so we can solve for A, right? So we can put this T back to this equation. And so what we have is mg minus T, which is I over R squared A, equal to ma. And of course, we can move all the A to one side of the equation and solve for A. And so we got A equal to G over 1 plus I over mr squared. Now you can see, because I over mr squared is always larger than 0, it is a positive quantity. So G over 1 plus that quantity is smaller than G. It means that the body, the yo-yo, is now descending at an acceleration smaller than the acceleration due to gravity. Why? Because it's being pulled up by tension force. The tension force slow down its sliding, right? So its acceleration must be smaller than the free fall acceleration due to gravity. So that makes sense, right? If the yo-yo has a very small moment of inertia, if I is 0, then this acceleration will approach that of the free falling acceleration due to gravity. Okay. Now for low slip condition, we always have alpha equal to A over R. The linear and the angular acceleration are related this way. Okay. Now because both the A and alpha, they are constant in this situation. Now see, the A is constant. So alpha is also constant, because A is just because the alpha is just A over R. So we can now apply the equation for uniform accelerated motion and uniform accelerated rotation to calculate the linear velocity, angular velocity, linear displacement, and the angular displacement. Okay. Now let us discuss a more difficult example. Now in the previous example about the yo-yo, we assume the no slip condition. alpha and A are related in a very simple way. But there are situations in which this relation does not hold. Now we are going to discuss one of this situation. It's about playing a snooker. Okay. I think some of you have already have tried to play a snooker before. Suppose you use a cube to hit the white ball in the middle. Okay, so you give the white ball a linear velocity, which I call V0. Okay, this is a linear velocity immediately after you hit the white ball. Okay, so the body now moves to the right with a linear velocity V0. Now, but the moment, the duration that you hit the ball is very short. So there's not enough time for the frictional force to produce a torque on the ball. So that essentially, after you hit the ball sharply, the ball does not have a rotation. So it only has a translational motion, but not rotation at the beginning. Okay, that is what happens in the beginning. Now, but when the ball slides on the table, on the cushion, now the snooker table is covered with a cushion, right? So there's a frictional force between the white ball and the cushion. And that frictional force is in opposite direction to the linear velocity of the ball, is opposite direction to the velocity of the center of mass, right? So this frictional force will tend to set the white ball into rotation. It tends to rotate the right ball in the clockwise direction. Okay. So eventually, what happens is that the linear velocity will decrease because the frictional force decelerate the white ball, right? But the rotational speed will increase because the frictional force produces a torque to speed up the rotation. Okay, now so that is a very special situation. Because the frictional force is opposite direction to the center of mass velocity, so it slows down the translational motion. But the frictional force produces a torque on the ball, so it speeds up the rotational motion. So the rotational motion is speed up, but the linear motion is slowed down, right? So that is a strange situation. Now let us draw a graph to see what would happen in the end. Now let's draw a graph of the rotational speeds and also the quantity R omega. Let's see what changes would it have with time. Now initially, if I draw a curve of V, we draw a curve of V first. Initially, the body has a linear velocity V0, right? And due to the frictional force between the ball and the table, the velocity decreases like this. Is that right? We assume the frictional force is constant. So there's a constant deceleration, and so the velocity decreases in a linear way. But the frictional force also accelerates the rotation. Now this is the curve of V, okay? And if I plot a curve of R omega, then when omega increases with time due to the torque of the friction, then the quantity R omega will also increase with time. And at a certain moment, which I call T0, I don't know what this time is, but let us call it T0. The linear velocity will be the same, will be just the same as the quantity R omega. So V is just equal to R omega here. Now what will happen later when V is equal to R omega? V is equal to R omega means there's a pure rolling. The pure rolling condition will satisfy. And in that case, the body will simply roll without any slipping on the surface. Okay, now at the beginning, there's slipping because the body is moving with a translational velocity without rotation. So there's a slipping. There's a relative slipping between the surface, between the two surfaces. And that slipping produces a frictional force to to rotate the object, right? But as soon as the rolling speed it is increasing, and it increased to the value of such that V is equal to I omega, the body now is rotating purely on the surface without slipping. And in that case, when that happens, the frictional force will vanish, okay? And the body will continue to rotate without slipping on the table. And so after the frictional force vanish, both the velocity and the angular velocity will not change. And V will be equal to R omega theoretically forever. Now, of course, this situation will not last forever, because in the actual case, the table is not actually smooth, and there are always some tiny up and down motion of the body due to the irregularity, the tiny irregularity on the table, and so there is frictional force acting on the ball, even if the ball is purely rolling. Now, but theoretically, if we consider two rigid body with negligible friction, that is a theoretical idealization, the ball will tend to roll on the surface forever. And that's why rolling can reach a much farther distance than sliding, because the frictional force between the body and the surface is now minimized. When pure rolling occurs, the frictional force is actually very small. So theoretically, when we idealize that no friction, the pure rolling condition will last forever. Okay. Now you are now required to calculate the time and the final velocity of the ball at this position. Okay, that is what you have to do in your homework. Now, but I will let you know how to do it. Not just tell you how to do it, but I will guide you how to do it. I stopped the sharing first. I shared it with you. Now let's see how to do it. Okay. Now you look at this diagram. The translational motion equation F equal to ma, right? Now F is a frictional force. The only net force acting on the body is a frictional force. We get the vertical force. We only consider horizontal force. And the frictional force tends to oppose the motion. So you need a negative sign, because now it's opposite to the velocity. So negative F is equal to ma. Okay, that is for the translational motion. And I deliberately make the quantity F positive. So when I add a minus sign, what I mean is that it is now decelerating the body. So A is now negative, meaning a deceleration in the translational motion. Okay. Now, for the rotational motion, the frictional force produces a torque. Torque equal to I alpha. The torque produced by friction is Fr, where R is a moment arm, right? So Fr is equal to I alpha. Okay. Now, you can actually solve for A and alpha. Now, notice that at the beginning, A and alpha, they are not equal. Okay. But they cause V, the linear velocity, to decrease and the angular velocity omega to increase. And with this A and with this alpha, you can calculate how fast V decrease and omega increase. And at what time you can equate V with R omega to find out at what time the V is equal to R alpha, R omega, at what time the pure rolling will occur. Okay, so now you are required to do that as a homework. Okay, now you can use the equation for uniform accelerated motion. You know, because you know the A and you assume F is a constant. right? So you can apply the equation for linear accelerated motion to find out the velocity at a later time. That allows you to find v. And you can also, because you know also alpha, you can also apply the equation of uniform accelerated rotation to find out how omega varies with time. And when you equate v with r omega, you got a time t at which the pure rolling condition is satisfied. Okay, so that allows you to solve for the time when pure rolling first occur, and you can now solve for the relationship between the v and omega at the rest of the motion. Okay, so you are now want to complete in your homework. Now, in this discussion, we consider striking, use our cube to strike the white ball at the middle. But in fact, there are a certain skill in snooker. I don't know if you have ever played snooker. If you strike the ball, the white ball at the base, below the center, okay, you will induce a backward spin on the white ball. Now, instead of just inducing a linear velocity to the right, you also induce a backward spin. Backward spins mean you see the torque, right? It will produce a spin in the anti-clockwise direction in this figure, right? Now, so what will happen then? Well, when the white ball collides with a color ball, say for example a red ball, when it collides with the red ball head on, okay, according to the law of conservation of linear momentum and energy, we assume the equation is the collision is almost elastic. The white ball will stop, and because the two balls have the same mass, so the white ball will stop in an elastic collision, and the red ball will take up the speed of the white ball and continues to move, right? Now, if the white ball does not have any speed, the white ball will stand still after the collision. But the white ball has some rotation. So when we transfer all the linear momentum to the red ball, it still has some rotation. And the rotation is in the backward direction. That rotation will tend to roll the white ball backwards, and so the white ball will be rolling backwards. Okay, and that is called a school shot. A school shot allows you to retrieve the white ball, allows you to the white ball to move backward after colliding with the red ball. So it will move to a favorable position for hitting another ball. Okay, so that is a way for you to control the motion of the white ball in snooker. In snooker, in 波樓我哋叫做扯褪後或者叫掹後. So the white ball will be moving backward. Now, if you hit the white ball on the top instead of below the center, if you hit the white ball above the center, you will introduce some rolling, some forward rolling motion to the white ball. And after you hit the white ball, hit the red ball, the white ball will be still rolling forward. And that is called follow through. Now, in this is a standard skill on snooker, which allows to control the motion of the white ball after hitting the other color ball. Okay. Now, we have some 學時學飛 for you to see. This is a long time ago. I can let you see this video. I'm sorry that the video is in Chinese, but I hope you can get the essential features of the video.
我聽講監製話要加多個女仔落嚟啊！嚇？加？我哋啲對白已經唔夠分量啦。梗係你啦，成日咁蛇龜，而家加多個人落嚟啦。會唔會係因為你嗰對長腿成日都唔 show 啊？哦，冇啲已經夠嘈啦，仲加多個嚇？你咯，究竟係加邊個啫？加邊個啊？邊個？有聲，冇人啊！有聲。嗨，咁多位小飛姐你哋好 ，Captain。
個女仔就係我。
哇！你玩咩啊？
係啊，今次我需要你哋幫手一齊去打桌球。
你識咩？
我唔識㗎，所以我需要你哋一齊對付佢。
黃子恒，喂，桌球唔係生得靚仔就識打㗎喎。唔係噃，聽講佢有桌球小王子之稱，好打得㗎。
點啊，咁多位是非精，準備好接受我嘅挑戰未啊？
都唔識打咯。
識打唔緊要啊嘛，我哋有嘅人未識啊。再加上我揾咗好多教練啊，教我哋唔使驚㗎。係咪好驚啊？而家你
快啲去學嘢先啦！
入咗，邊個咁厲害咧？佢就係吳安儀，今年連奪2個世界錦標賽冠軍，係香港首位雙料 Q 后啊！
喂，係我揾咗你哋教練啊，就係佢啦。
你係小儀啊？係，我都係小儀，不過我係4眼嘅吳安儀。
咁硬嘅，我哋都係儀啊！我哋有友誼，於世上有幾個知己。
你3個唱得咁難聽，
係啊，
色、黃色、粉紅色，佢哋一 Q 打晒你哋入袋。好，
黃色啊！一次過打入3個波，咁牙刷，我就唔信啦！世界冠軍都係咁話。哇！一 Q 清袋 ，Q 后果然犀利啊！勁啊！
其實咧，一次過入3個波咧，係純屬係表演性質嚟嘅。實際上咧，呢個係包。所以而家我哋會試下咧，睇下喺桌球桌球上遇到嗰啲比較刁鑽啲嘅波。
咁啊，唔好講咁多啦，我哋一齊學嘢啦。
好。
黃教練將唔同顏色嘅波擺喺台上唔同位置，嚟模擬比賽上被對手 set 波嘅情景。咦？白波要撞入紅波，但係綠波同埋藍波阻住晒喎，點打啊？
睇到咧嗰個白波嘅位置咧，其實係封死咗好多路。而家安儀咧就會示範一次咧，利用3個箍去打入呢個紅波。呢個純粹係佢平時練習。係啦。
靜啲啦，唔好騷擾安儀啊！哇，真係是非精史上最靜嘅一次啊！我淨係聽到啲波聲咋，咁入唔入到啊？好高興認識你啊！
你哋冇嘈住啦，俾教練講下究竟呢一球嘅技巧喺邊度？
好。
教練，
頭先安儀示範嗰球咧，其實係純屬佢嘅平時練習翻嚟對啲角度嘅知識嚟嘅。
識基本嘢啊嘛。
係最基本用3個箍，即係佢識睇個 angle 咧，就可以打到呢個波㗎啦。
咦，你咁講真係有啲高難度啲喎。
可以示範㗎。嗱，而家我哋就要打中個白波，擊中呢個紅波。
黃教練俾 tips 我哋，話今次撞台邊2次就可以將紅波撞入袋啦。
教練，我準備好啦。
好，
唔好講咁多嘢。
啊，你呢個桌球小王子咁大口氣，啊，你真係入到嘅喎。到我哋啦，啊，擺靚 pose 緊要啲，靚湯小心坐冧張台啊！阿你唔打得都睇得啊！
你示範下。
我準備好啦。
入白波嘅，我都入唔到啊！
我準備好學嘢啦。
嚟啦，開心唔開心？
好，而家到 Q 後出馬。
黃教練啊，點解咧頭先佢哋打嘅角度好似一樣咁，但係咧安儀就入到，但子恒就
因為只係好似一樣咯，
唔係真一樣。
咁大家都睇到其實頭先個台面嘅局面咧，阿子恒咧單憑一個自然嘅角度咧，係冇辦法做到一個效果出嚟嘅。咁啊，一定要用啲 Q 法嘅。咁啊，安儀咧就係利用咗下旋仲係要重下。
So that the school shot.
將個角度拉闊咗。
She hit the ball at the base
呢個都係桌球上一個
to induce a backward spin. So the angle of refraction will be smaller than the angle of incident.
為咗贏黃子恒，大家繼續練習啦。嚇，嘉琪打完1下就走咗啦。心穎係運動叻啲，但都係打唔入喎。你睇人哋又打入啦，實力真係差太遠咧。點算啊？
你班是非精，投降吧啦！
佢好囂啊而家。
可以咁樣嘅，黑心。雖然佢靚仔啫，我哋唔可以驚佢嘅。好，我哋有第二個教練啊嘛。係。我哋嘅教練喺嗰度。
我喺度。
湯博士，又係佢啊！湯博士，運動環節喎，打桌球都關你事，其實你係咪暗戀我啫？
梗唔係啦，打桌球都有物理學噶嘛，你唔學物理點打桌球咧？
咁你教我啦，嚟，
唔好淨係教你嘅，我哋齊跟阿湯博士上一堂先啦。
嚟啦！湯博士 OK 啦。
湯博士，波就已經 set 好啦，咁究竟桌球有咩物理咧？
嗱，其實咧桌球不外乎都係將個白波撞個顏色波落個袋度啫。嗱，如果個白波係正撞落個顏色波度，如果白波係冇旋轉嘅話咧，咁根據呢個動量守恒定律同埋能量守恒定律咧，個白波撞完個紅波之後咧，就會停咗喺度唔喐噶啦。個紅波咧就會好似白波之前個速度咁樣走落個袋度啦。
哦，哎呀，但係我唔係好明啊。
哦，
不如你出去示範一次，俾我睇睇啊。
好。
嗱，其實咧，子恒頭先打嘅咧就係喺個白波嘅中間，呢一個幾乎咧係一個完全嘅彈性碰撞，咁所以個白波咧就會將佢所有嘅能量咧傳遞晒俾個紅波喎。於是白波撞完紅波之後咧就會停低，而個紅波咧就會用白波先前嘅速度咧向個袋邊走啦。嗱，子恒啊，不如你試下今次打個白波嘅上邊睇下發生咩事啊？
好。
其實咧，你頭先打完個白波之後咧，當佢撞擊咗紅波之後，佢仲向前流動嘅喎。嗱，咁其實咧，白波嘅運動咧有兩部分嘅，一部分咧就係向前直線嘅運動，另一部分咧就係當你支 Q 打到白波嘅上邊嘅時候咧，其實佢係向前嘅旋轉運動㗎。咁當佢撞完個紅波之後咧，冇錯，佢係將線性嘅運動嗰部分嘅能量俾晒紅波，但係因為佢之前咧仲有一個旋轉運動喺度啦，所以咧佢就會向前咁樣滾動啦。咁所以咪向前流咯。
聽完博士咁講，今次試下打白波嘅底部啦。白波同紅波碰撞之後，先會停低，但係因為白波有後旋，佢同台面嘅摩擦力就會令佢向後滾動。
透過呢個原理，學識控制白波唔同嘅走向，咁打桌球就得心應手啦。
講完碰撞之後，聽講有種技術叫撞箍，連桌球小王子都話未必打到喎，究竟有幾難呢？
咦，咁 Sammy 得唔得咧？
哎呀，好難下喎。
即係點解？
嗱，你哋咧仲未明白呢個入射角等於反射角嘅原理。好，等我攞塊鏡出嚟先。
你俾我哋照㗎？佢想我哋望下啲靚嘢。
唉，梗係唔係啦。其實咧係俾你練習咧點樣去對個入射角等於反射角。嗱，嘉琪啊，你而家試下咧打呢個白波，但係咧要對準鏡裏邊嗰個紅波嚟打喎，睇下打唔打中啊？
咦，咁樣又好似易啲喎。你得㗎，我睇好你。係。Yes！ 湯博士，點解呢個方法會易咁多嘅？
嗱，其實咧呢塊鏡咧就反射咗張台嘅影像喎。當有塊鏡之後咧，成張台咧就好似反轉咗咁樣，形成咗一個影像啦。咁所以咧，當入射角等於反射角嘅時候咧，其實啊呢個紅波同埋呢個白波咧喺塊鏡裏邊咧就成一條直線。咁你對準個紅波反射嘅時候，咪打到咯。
You try？俾得我實得啦，什麼事啫？唉。
All right, so that is the video. You see how the spin is in action, right? Snooker is just about the translational motion, but also about the spin. The spin is important for controlling the eventual motion of the white ball. Now, so let's start.